Rocket gimballing systems pivot or swivel a rocket engine's nozzle to redirect its thrust, which provides active steering and stability. By shifting the force away from the rocket's center of gravity, the system generates rotational torque, which is the force that allows objects to spin around its axes. In this video, we will be exploring how rocket gimballing systems steer the rocket, components of a gimballing system, history of the gimballing system, alternatives to the gimballing system, and rockets that are famous for their gimballing system. In a gimbal system, the engines or exhaust nozzle can be swiveled around the two axes, known as pitch and yaw. You can visualize pitch and yaw using your fist. Pitch is when you tilt your wrist up and down. Yaw is when you tilt your wrist sideways. And there's a third axis known as roll, where you rotate your wrist. A gimballing system steers the rocket by rotating its engine nozzle. This redirects the powerful exhaust thrust away from the rocket center line. When the thrust points sideways instead of straight down, this creates a rotational force, also known as torque. When the nozzle is tilted to the left, the thrust line is at an angle to the center line, also known as the gimballed angle. As the thrust no longer passes through the center of gravity, a torque is generated, and the rocket's nose turns to the left. The same thing happens when the engine nozzle turns to the right. Modern gimballing systems have accelerometers, gyroscopes, and mounting frames for precise reusability and vertical landings. Accelerometers measure linear changes in speed and physical forces. The rocket's computer uses this data to track position and velocity, detect deviations from the planned path, and commands the engine gimbals to tilt the thrust vector and steer the rocket back on course. Gyroscopes act as core orientation sensors. They use a fast-spinning wheel to maintain a fixed point in space. When wind or other forces push the rocket off course, the rocket body moves, but the gyroscope's internal axis stays still. Sensors measure the physical difference between the tilted rocket and the stable gyro, and send signals to motors that swivel the engine nozzle to correct the flight path. Mounting frames in a rocket gimballing system hold the engine securely while letting it move. They connect the engine to the rocket body, support heavy thrust forces, and handle the torque needed to turn the engine for steering. Rocket gimballing systems evolved from early jet vane deflections in World War II to pioneering pivoting engines by Dr. Robert H. Goddard in 1937. They were first implemented in the MX-774 in 1948 and the Martin Viking rocket in 1949, paving the way for multi-axis thrust vectoring on launches like the Saturn V and Falcon 9. Dr. Robert H. Goddard was an American physicist, engineer, and inventor, often known as the father of rocketry. By launching the first rocket with a motor pivoted on gimbals and controlled by a gyroscope mechanism, this innovation allowed active flight steering and dynamic stabilization, advancing his earlier work with fixed exhaust vanes. The German V-2 rocket, which was used during combat in World War II, used 4 fragile graphite vanes placed directly in the exhaust plume of the rocket motor for thrust vector controlling, rather than a movable engine bell or gimballing the engine. The first true gimbaled rocket engine was flown on the MX-774 research rocket on July 14, 1948, at White Sands Proving Ground. It was the first U.S. research project, and the rocket was designed as an intercontinental ballistic missile. Built by Convair, the rocket featured 4 swiveling combustion chambers for directional control. The Martin Viking rockets were a series of 12 large liquid-fueled sounding rockets, built by the Glenn L. Martin Company for the U.S. Naval Research Laboratory in the late 1940s and 50s to replace the captured German V-2 rocket for upper atmosphere research. The first rocket flew on May 3, 1949, from White Sands, New Mexico. It used a gimbaled thrust chamber moving on 2 axes for pitch and yaw control. This design replaced old exhaust vanes and improved steering during flight. Larger rockets like the Saturn V, which you can learn more about in my Saturn V video on my channel, and Space Shuttle used hydraulic actuators to move the engines and steer the rocket. High-pressure oil pushed heavy metal arms to point the huge exhaust plumes in the right direction during launch. While liquid rockets gimbal the entire engine bell or assembly, solid propellant missiles later evolved to use flexible elastometric seals or ball joints to swivel just the nozzle. This helped eliminate the heavy, complex hydraulic actuators and flexible propellant lines needed to swivel the massive liquid engine bell. This saves critical weight and space. Modern reusable rockets, such as those built by SpaceX, push gimballing precision to high limits by relying on rapid, active actuator corrections to stabilize boosters during vertical landings. Although most rockets use gimballing thrust systems for steering, many smaller rockets use other methods for stability and control, and can also be used alongside the gimballing system. The three methods we will briefly explore are movable fins, vernier rockets, and thrust vanes. Early rockets and air-to-air missiles, which are missiles fired from an aircraft used to destroy another aircraft in flight, use movable fins attached to the rear of the rocket. When the fin tilts, the rushing air pushes it sideways. As the fin is away from the center of gravity, a small tilt creates a large torque that moves the rocket. Older rockets, such as the Atlas missile, used additional rocket engines attached to the bottom of the main engine to generate torque. These rocket engines are called vernier rockets. These are used to make precise, fine adjustments to the vehicle's altitude, velocity, or roll when main engines are too powerful or lack enough steering control. The rockets use gimballing to steer the rocket smoothly. On some early rockets, such as the V2 or Redstone rocket, small thrust vanes were placed in the exhaust stream of the main rocket to deflect thrust and produce a torque. These vanes tilt to force the exhaust gas to move sideways, which steers the rocket without needing to swivel the heavy main engine nozzle. These are usually used during liftoff, at high altitudes, or low speeds, when movable fins cannot be used as there's not enough moving air around the rocket. We briefly mentioned Saturn V, the Space Shuttle, SpaceX Falcon 9, and the Martin Viking rocket previously for their gimballing systems. We will now explore why the gimballing systems in these rockets are so popular. The Saturn V rocket's gimballing system was so popular because it used massive hydraulic actuators to power directly by the engine's own high-pressure kerosene fuel to pivot four F1 engines, which have 1.5 million pounds of thrust each, steering a 36-story vehicle with high precision. It redirected colossal physical thrust, pivoting four outer engines up to 5 degrees to control for pitch, yaw, and roll against high-altitude wind shears and dynamic pressures. The Space Shuttle's gimballing system was so popular because it provided high-angle thrust vector control to steer a massive asymmetric heavy-load vehicle during intense atmospheric ascent, dynamically shifting its thrust direction to compensate for a rapidly shifting center of gravity as the fuel burns off. The three Space Shuttle main engines, which are these three right here, featured an unusually wide gimballing range to manage severe aerodynamic forces and off-center weight, and they control pitch, yaw, and roll dynamically during the entire climb to orbit. SpaceX Falcon 9's gimballing system is so popular because it uses high-pressure liquid propellant, RP-1 kerosene, directly as its hydraulic fluid. This clever design choice eliminates complex, heavy, independent hydraulic loops, saving massive amounts of weight and parts while enabling pinpoint precision for landing reusable boosters. The system routes high-pressure rocket fuel from the rockets. Oh my god, am I losing my voice? System routes high-pressure rocket fuel from the engine's own turbopumps to swing the engine bells, avoiding dedicated fuel tanks and separate service loops. The Martin Viking rocket was historically significant because it was the first US rocket to use a fully servo-controlled, two-axis gimbaled engine for active steering. This replaced the fragile, inefficient, graphite exhaust vanes used by the V2 German rocket. Swiveling the entire thrust chamber avoided the aerodynamic drag and unwanted consequences created by stationary stabilization fins. It also allowed smooth, active pitch and yaw steering, driven onboard by gyroscopic guidance. Thank you for watching today's video on rocket gimballing systems. Next video, we will be exploring rocket engine turbopumps. Don't forget to like, subscribe, and hit the notification bell to never miss a video.